Hello friends. So today we will learn about the Djikstra algorithm. The Djikstra algorithm is basically used to find a single source shortest path. Single source shortest path means that we have given many locations as in this graph. Let's say these A, B, C, D, E, F are the vertex of this graph, and our interest is to find the shortest distance from any of the given vertex. So let us say the B is the source for us. So we are interested to find the shortest path from B to A, B to C, B to D, and B to F. So if you want to find a shortest path from a single source, the Djikstra algorithm is mostly used. So before going to the algorithm of the Djikstra algorithm, we will understand some basic concept of this approach. So let us understand relaxation. This is a very primary concept used in the Djikstra. Relaxation is something that keeps on improving the distance of any vertex from the source. So in this process, what we are doing, we are assigning one d value, you can say distance value of the vertex from the source, and during the process we keep on changing these values if this value is going to improve. What does it mean? It means that any point of time the d value of u is 5 and d value of v is 9, and if we find any path from u to v of weight 2, then you can see that 5 plus 2 is going to less from 9. So we are going to relax this. Relax means we are going to change this value, and this value will only be changed if it is going to decrease. Now let us take this example. Let's say at any point of time the d value of u is 5 and d value of v is 6, and if we have a path from u to v, then 5 plus 2 is going to increase, means more than this d value, so we are not going to change this. So d value is going to change only when the d value of v will be more than d value of u plus the weight of this edge. Means if the d value of v, means if this is 9 which is more than 5 plus 2, then only we are going to change. What we are going to change is we will keep this value u plus the weight of this edge, that is 7. And at the same time, whenever we are going to change, we need to change its predecessor, that is called parent. Now what does this mean? It means, for example, we have this scenario, we have this something like this. Let's say we have vertex A, B, and C, and let's say the D value is given to us. This is 6, this is 9, this is 1, this is, let's say, something 7, and at the same time we have some more information. We are writing here the D value of B is 9 and the predecessor of B is C. That means that if you want to go to this vertex, so far we have known the path which is coming from C. Means if you want to go here, we have to go from this path, means from the vertex C and plus 2, that is 9, and this path is actually not yet been seen. So when we process our algorithm, let's say we have found one path from A to B, and we need to decide that which path is better to B. Either we have to go from C to B or from A to B. So how can we find this? We keep on checking this relaxation procedure. So here we find that the D value of A is 6. So this is actually 6 here, 6, and the weight is 1. So this makes 7. And the D value of B, which is 9 here. So 9 is more than 7. So we need to change this. So what we are going to do is we will change this value and we will make it 7. That means we have to update these both information. We will be writing that the new d value of b is 7, and this is possible to the path A. That means the next time we are updating this information that the distance to B node is 7, and we will be going through the vertex A, not from C. So every time whenever we are going to change this t value, we need to also update its parents. Parents tell us that how you are reaching to this path. And then other important part is when we means apply that algorithm, we will be having the d values at each vertex. So if you find that the the vertex contains some value, and if it is not infinite, then that means there is a path possible. If you find any graph in which there is some infinite value is means present, that means there is no path available from source to that vertex. For example, if I make a graph like this, a b and see something like this. So means when you apply the Djikstra algorithm, and our interest is to find the path from A to B and to C, then at the end you may find that you may find some values here, maybe 1 2 3 4 9 something, whatever, let's 9, and here maybe infinite. Now what does this says that if the value is infinite, that means that there is no possible path from A to C, and you can see from this figure that you can go from A to B but not to C. So at the end, when you find the d value is infinite at any vertex, that means that vertex is not possible to reach from the source. So this is the Djikstra algorithm. So we'll have a look on this algorithm, and then we will apply the algorithm to solve one numerical. So the first thing, important point you need to remember is that it is not applicable for the negative weight edges. Means if any of the means if this is a graph and if contains 2, and if it contains something, let's say 9 minus 9, then we will be not using Dishita algorithm. Then we will be using some other algorithm like Bellman Ford. The Dishita algorithm basically is used for the graph which contain positive edges, though it can work for negative edges if the negative edges is from the source, but we are assuming that it is not working for the negative edges. At this point we are assuming that it will not work for negative edges. So what we are doing here in this algorithm, maintain a set S of vertices whose shortest path from S has been determined. So here we are having two sets. One set is S and one set is Q. So initially the set S is empty. We will be this is set is empty, and Q is a set which contain all the vertices of the graph. So let's say we have four vertices in the graph. So A, B, C, and D. So what we are doing, while Q is not equals to empty, extract min Q. So what we are doing here, we have in the Q set we have the vertex, and as I already told you that the vertex here in the graph will having some d values. So let's say the d value of this is 2, this is 1, this is 3, this is 6. So what we are doing, extract min. So this procedure extract min is actually extracting the vertex which have the minimum d value. So if this is the situation where we have four vertices with these d values, so if I apply extract min, then this will be the answer, because this is the vertex with the minimum d value. So what we are doing, we will apply the extract min, this vertex will be returned, and this I will be adding in this set S, means this vertex is included in our path. Similarly, we keep on doing this way, and next time again we will find the minimum d value vertex, and we keep on improving it and removing from the queue. So we keep on adding these vertex from the queue to the S set, and when this queue set become empty, we will be stopped, and that means the process should stop and we are reached to the solution. So let us see how we will find the solution. We'll take an example. Let's say this is example given to us. So before we start the procedure, we need to do some initialization. So what is the initialization? We must first know what is our source. So in this case, we are assuming that S is our source, and we are interested to find the distance from S to U, V, X, and Y. So one more assumption we need to take initially, that the for the source the d value at the source is 0, and the d value for all other vertices is assumed to be infinite. This is an assumption we need to take initially. Then what we do, we will make a kind of matrix which will be keeping all the d values of all the vertex. So let's say we have vertex S, we have U, we have V, X, and Y, and these are the dv values. So initially we have 0, infinite, infinite, infinite. This is called initialization process. Now whatever the vertex we are selecting, so initially we have to start from the source s and we have to look to the neighbors of this s. So the neighbors of this s is u and x. So we will be relaxing this particular vertex. So if you look at this, the d of s is 0 and s to u path is 1. This is the weight. So if you see the d value of u, the d value of u at this instant is infinite, and you can see that this relation is existing here. Du is equals to d of s plus su. So here this is infinite and this is actually 0 and this is 1. So infinite is more than 1. That means we need to relax this d value of u. So we are going to change this d value, which becomes 1, because 1 is less than infinity. So whenever you find any new d value which is less than the previous d value, we need to update it, we need to change it. So from s we can go to u, from s we can go to x. So from x, here also the same situation is here. This is 0 plus 5, this is 0 plus 5, which is less than the infinite. So we are going to change this value. At the same time, we need to keep a note of the predecessor, how you are going. So to u I am reaching from s, to x I am reaching from s, and this we have no path. Now the next step is we need to find out of these which is a minimum. So we have now we are applying the extract min procedure. Now we are applying this procedure, extract min from the set q, and this procedure will give you the vertex with the minimum d value. So we have d value 1, infinite, infinite, 5 and infinite. So this is minimum, so it will return this u. So we will add this s, add this u in the set s. Now once you have means confirm this vertex in your path, then we will look to the neighbors of this u. So from u you can see you can go to v. Now v is actually infinite, that means we can improve this d value. So we can improve, this is 1 now, this is 1, and 1 plus 1 is 2. So you can improve this to 2, and this you have reached from u. Similarly from u you can go to x. Now x d value is 5. Now we can see we can reduce this value or not. So you can see 1 plus 2, this is 3. So that means the 3 is less than 5, so we can further reduce this. So you can reduce this to 3, which is coming from u. And we look at the y. To y there is no path, so we cannot change its value. So now we have to look to the extractment procedure. So we have 2, 3 and infinite. This is minimum, so we will take this 2, we will take this 2, and then we will look at the neighbors of v. So the neighbors of v is, one is y. So the value at v is actually what? The value of v is 2 here, and you can take the weight of this edge is 4. So 2 plus 4 is 6, which is less than the infinite. So I am going to change this to 6, which is from v. The other possibility from v is we can go to y, we already have changed, we can, and there is no other path. So again we apply the extractment procedure. Extractment procedure will look to the vertex, what vertex is left, x and y is left, and we look to the d values of x and y. So this is minimum, we will take this x and write in the set s. Now from x we can go to y, we can go to u. and we can go to V. So we have to check that is there any possibility to reduce the D values. So from X to Y, if I go, so X is what? X is 3, this is 3, and 3 plus 2 5. Now the Y value we are having is 6, so this is actually possible to reduce. So I am going to make it 5, and this is through X. Now we'll see this. Now from X to V, now V is 2, this is already 3, we cannot going to improve it, so we will leave this. Then this is U. Now U is 1, X is 3, we are not going to improve it, so we'll leave it. So that means we cannot further improve it, and our process stops here, because the next only one vertex is left. When you apply the extractment, this is the only option, and this will be returned and added to the set S. Now the Q set is empty, we have to stop the procedure, and at last you can conclude by this. So you can write this is actually 1s, this is 2u, 3u, and 5x. What does it mean? It means that from the source, if I want to go to u, it will take 1, the cost is 1. To v, the cost is 2. To x, the cost is 3. To y, the cost is 5. And what does this tell? This tells us the parent, how you're going to use. So if I'm going to from S, if I want to go to U, this is through S. Through S I can go, and this will be of path 1. Now to V, I can go in cost 2 from U. So from V means to V, I can go like this, and to X I can go in cos 3 from U. So from U I can go to X, so this is actually 3, and to Y I can go from X. So from X I can go to Y, and the cost is 5. So 2, 3 plus 2, 5. So this is the answer. So S to U is 1 distance, S to V is 2 distance, and S to X is, you can write here, this is 1, this is 2, this is 3, and this is 5. This is what we have summarized the result. So this is how we can apply the Djikstra algorithm to find the shortest path. So hope you have understood this algorithm.